Hi, y'all. I'm Dr. Jennifer Puetzer, and I'm an assistant professor here in the Department of Biomedical Engineering and Orthopedic Surgery. And my lab specializes in musculoskeletal tissue engineering. In particular, we are interested in trying to create replacements or drive repair of the meniscus, which is this little pad-shaped disc here in the knee that helps to distribute load, and of course tendons and ligaments, which attach our bones and muscles throughout our body to allow our skeleton to move. And what these tissues have in common is that they're composed of these large collagen fibers that run the length of the tissue. And these are really what provide all the strength and function to these tissues. So whenever we have an injury or a tear, it breaks those collagen fibers and makes it so these tissues are no longer functional. Unfortunately, the cells in these tissues are quite lazy, and so we often do not see these collagen fibers regenerate in any way, resulting in more than 1 million surgeries a year to repair or replace them. And so we're really interested in trying to create replacements for these. And in order to make a functional replacement, we really have to go after getting the natural hierarchical structure of collagen. And this is really just the organized ordering of collagen fibers in order to make them really strong. So this basically starts with the tropocollagen molecule, which cells will spit out into matrix. They then will start to group this into fibrils, which are often in the nanometer diameter range. These will group together into fibers, which are a micron level range. And then finally, in our really strong, highly loaded musculoskeletal tissues, we see cells group these into hundreds of microns, millimeter diameter fascicles. And so the field's pretty well versed on how we can get this fibril level organization, but it remains much of a black box of how do you move to these larger fibers and fascicles. And that's really where my lab sits in trying to understand how can we regenerate those or make them in vitro to create engineered replacements. We do this primarily using this system here, where we take high density collagen gels, we mix cells into those gels while it's still liquid, cast it into a sheet gel, cut out little rectangles, and then by culturing in this system here, we can basically screw down, clamp the edges of this, and this in turn harnesses the natural contraction of our cells and gives them mechanical cues to basically tell them to align and develop fibers across the tissue this way. This is a little bit of what this kind of looks like, where here the gray is collagen and green is cells. So at 0 weeks, we're completely unorganized. By 2 weeks, we get this nice alignment of fibrils throughout the tissue. By 4 weeks, we get this developing into larger fibers. And then finally, by 6 weeks, we start to see those larger hundreds of micron wide fascicles forming. So this system we're really excited about. It gives us some really nicely well-organized hierarchical fibers and gives us the opportunity to really start to use this as a benchtop model to ask lots of different questions. And so in our lab, we kind of concentrate into 3 different areas. These, again, all kind of revolve around using the system to drive our hierarchical collagen fiber formation. And then we're interested in looking at how can we make those fibers become bigger and stronger. We're also interested in how can we start to integrate these tissues into bone. So anywhere there's a tendon or ligament in your body, it has to anchor into that stiff bone, and that mismatch in mechanics can lead to lots of injuries. And then we're also interested in how do these tissues change with age? And of course, how can we start to mitigate those changes to reduce the injury and the inflammation that we often see with aging in these tissues. And just to kind of highlight 2 things that are a little more pharmaceutically relevant, within our fiber development, we're really interested in understanding the natural cross-linking of collagen fibers, which this is all regulated by the enzyme lysyl oxidase. It will form these kind of weaker divalent cross-links, and then for reasons unknown in our really strong, highly loaded tissues, we see these develop into really strong trivalent cross-links. So we're doing some work to really understand what drives that change, and how can we reproducibly get those strong cross-links over and over again so that hopefully we can either have a pharmaceutical or a physical therapy routine that can drive cells to do this after injury. And then in our aging work, we're really interested in the accumulation of these non-enzymatic cross-links called advanced glycation end products, which can cross-link anywhere in our collagen structure, here represented by the little starbursts, and they're thought to really stiffen our tissues and lead to more injuries. So we're interested in looking at, is there a way that we can really mitigate, keep these at bay, and keep our tissues healthy and strong, and not having this inflammation that comes with aging. So again, using pharmaceutics to either break those crosslinks or mechanical stimulation to drive cells to break them down themselves. And so with that, I'll just leave you with a little bit outdated picture of our lab. And of course, if you're interested in the lab or have any questions, feel free to email me here at my email address. And thank you.